Hi, so for the next section of Chapter 7, we're going to take the idea of area and actually kind of springboard from that and create a volume of a solid of revolution. So we're going to do that by taking that region R, wherever it is, right here I have it shaded and kind of noted for you. We're going to spin it around a line, and that line could be the x-axis, it could be the y-axis, it could be some other vertical line or horizontal line, but you kind of have to imagine like this one region spinning around that line, and it would create a totally enclosed solid object. So what we have here is, I'm going to read it in like two steps, and really I'm going to first set out by trying to understand what the region is. That's really important. That's step one. And then we'll figure out where we're rotating about and what method we're going to use. So for this video, we're only going to talk about the disk method, but there are two other methods coming down the road. So I'm going to describe each one of those, and you're going to choose the one that works best for the region that you have and the solid that you're creating. So the region R, as you can see in this picture, is already defined for you, but I want to kind of just talk it out. It's the region bounded by y equals x squared, which you see here. That's our parabola. The x-axis, which is, well, right here. Okay, that's one of your boundaries. And the line x equals 2. So remember, vertical lines have x equals equations, and horizontal lines have y equals equations. So that's why I have this region R shaded already for you. Now, what I'm going to do for that is now I'm going to actually consider, well, where am I spinning? What kind of solid am I going to create from this revolution, from taking this region and spinning it around some location? So again, we had three boundaries, y equals x squared, the x-axis, x equals 2. And then I sort of like, I don't know, kind of highlight this word about. Now I care about where we're spinning. And we're going to spin around the x-axis. So I usually think about the spinner as being bold. I like to put it in my drawing here. So I'm going to kind of overlay over the x-axis, which was one of our boundaries, by the way. And I even put like a little spinner on my picture, like, hey, here's where we're rotating against. And so if you can imagine taking this weird curvy triangular-ish section here, this region, and spinning it around this line. That's why you see this like weird blue line here at the bottom, because if I take that and I spin it around the x-axis, what you're actually going to create is sort of this like funnel looking thing, which has a circular base on the right hand side. I just like to kind of imagine like, well, what am I actually creating? This is a closed solid, it is a closed, filled in, with cement kind of funnel in a way. And I want to find the volume of this three-dimensional object. So we're taking a two-dimensional region, and when you spin it around that axis, you're creating that third dimension. So I'm going to kind of undo some of those lines that I made just because I want my image to be good. And so what I'm going to do, just like we did in area, is I'm going to be drawing in a rectangle. And I'm going to draw this rectangle in a particular way. Actually, let's do that now. When you're doing the disk method, you're going to draw a rectangle in the shaded region that is perpendicular to the axis of rotation and actually also touching the axis of rotation. So that's what you see over here. I'm going to do that. It doesn't matter where in the shaded region you draw it, but I am going to draw that. There it is. Okay, nothing special about the exact location, but I definitely have it in the shaded region. Notice it's not down here. Okay, it's just in that shaded region, and it's perpendicular to the axis of rotation. And there are certain things that are consistent in this picture, right? Because here I have this rectangle. I'll just kind of outline it here a little bit. The top endpoint is always on your parabola y equals x squared. No matter where you move it, left or right, that top endpoint would be on that parabola. The bottom endpoint of that rectangle is always anchored to the x-axis, right? So that's part of your region, and that's consistent. That's great. and you're looking for consistency here, if you can draw a rectangle in the shaded region perpendicular to the axis of rotation, and it's touching the axis of rotation the entire time, then that's how you know you are in the disk method. That's going to be your best method to employ. So what I have over here, this weird image over here, is just, again, trying to be clear about what did you just create. This is imagining that rectangle kind of spinning around the x-axis. Maybe I'll try to change the color here. What you actually create is you create a disk. You know, I'm just trying to kind of imagine that. So that's what this picture is. It's basically taking that rectangle, spinning it around the x-axis. You actually create this disk, or really what it is a cylinder. So I'm just going to kind of put that axis of rotation through there. And a disk is the same thing as a cylinder, really. So what I want to do is talk about the volume of a cylinder. I want to sort of develop what the disk method formula is grounded in. It's really geometry. You don't have to prove this to me, but I definitely want to show you where it comes from. So what I'm going to do is take the cylinder, which is an awkward orientation. When you guys were in geometry, you probably did not see a cylinder presented like this, you know, a tuna can on its side. What I'm going to do is just draw it a little bit more, maybe the way you're used to seeing a cylinder presented in a geometry textbook, which would be something like this, and it has some kind of center to it. Okay, now I'm going to put the axis of rotation through it, so I'm really just changing the perspective from this image to this image. So what you're actually doing here for the volume is you're kind of taking the idea of a Riemann sum. You're going to say, you know what, if I had that rectangle and I spin it along the x-axis, I would create this cylinder. What if I broke up this region into, let's say, 6 cylinders? You know, I could just basically add up the volume of those 6 cylinders, and I would have a good approximation to the volume that we've created. Now, we're not going to do an approximation. We are going to get right to the exact value, but I want to sort of demonstrate it this way, that look, if I'm going to find the volume of this disk, which is really a cylinder. Well, the volume of a cylinder is really just the area of a base. I mean, I can tell you what the formula is, I will, but it's really just the area of the base times the height. That's kind of how most volumes are constructed. So a cylinder then, the formula for the volume of a cylinder is the area of the base, which would be the circular part here, which is, well, has a radius, r, and so the area of the base is 2, I'm sorry, not 2, it's pi r squared. Pi r squared. And then, you know, for the height of it, well, I'm just going to have to label that. That's the height. Some kind of little width there from our region creates this height on the side. So I'm just going to kind of multiply those. That's the volume of one disk or one cylinder. So if I were to take that idea of a Riemann sum and really run with it, if I wanted to find, you know, the total volume of the solid that you're creating in this revolution side, right, then I would just add up a bunch of these cylinders. And a bunch obviously is a vague term. 6 cylinders, 10 cylinders, 10,000 cylinders, right? And the point is you want to make these cylinders so paper thin you can't even see them. That's how you're going to get the exact volume of this solid. So if I want to do that, well then what I would like to do is I would like to make sure that the height of that cylinder is really, really small, that height is going to go to 0. So I'm going to say that. And the moment that you have, just like with area, you have a limit as h goes to 0 up against that sigma, that's sort of what creates the integral. And that's how you're going to get the exact volume. So when you're doing the volume of the solid, and I'm just going to say by disk method, I'm going to show you a couple of things. So we're definitely going to turn this into an integral. And so this sort of combines to give you your integral sign. And I have, you know, the pi r squared. And instead of this h, let's actually fly back and let's describe this a little bit. So let's sort of go upwards here. Here's my h along the side here. But if I go back to this picture, Well, that's h. And if I kind of go all the way back to this picture, your h is really some delta x value, some kind of small change in x value on this region. So I'm going to fly back down to where we were working and say, you know what, it's a delta x. I'm going to make this integral a dx. That's what kind of transforms that dimension. And I'm even going to put, that's going to happen if you happen to draw your rectangle in a vertical presentation. Okay. I'm going to have another formula for the volume of a disk method. And guess what that's going to be? A dy. Now that is going to happen if you happen to draw your rectangle in your shaded region and it happened to be in a horizontal presentation. So these are the two things I want you to kind of know about the disk method. This is your formula. This is what you should know and be able to do. It's right here. So you can just memorize it, and I could have just told it to you, but I want you to know it really comes from the volume of a cylinder. All right, now you certainly do not have to have the pi inside the integral. A lot of times you'll see textbooks write that pi outside the integral. It's totally up to you of what you want to do. I think I generally tend to putting the pi outside the integral as well. But let's go through this kind of base model here. Remember how powerful the dx and the dy is. When there's a dx in your integral, not only does that tell you that your whole integrand has to be in terms of the x variable, but it also tells you that you get your limits of integration from the x-axis. That's your start and stop. And same thing if you have a dy integral, that means your whole integral is in terms of y. That's, you're going to see a lot of y variables inside there. And you get your limits of integration from the y-axis. So that's really important to sort of make sure that you're taking a look at. So that's the development of what the disk method is. This is what I actually want you to know and sort of study in a way. So let me get rid of all that green so you have something good to look at of what you should be remembering. So we're going to come back to this question now. I mean, I'm actually going to work on this problem using what we have here. So I'm going to try to, hopefully, get rid of some of those pictures there. Okay, so here we have that rectangle again, just kind of thinking about what we had done. We drew a rectangle perpendicular to the axis of rotation. It's touching the axis of rotation. And so there's our imagery. Let's think about how I'm going to do this. I need to think about this in terms of like, what's the R and what's the H and all of that kind of stuff. So if I mark up my picture, which I'm going to do, your R is basically the length of the rectangle. So what that means here, think about it, it's top minus bottom. That's how long that rectangle would be. So I'm going to kind of put that. And the reason it's top minus bottom is because I drew this thing in a vertical presentation. Okay, so top minus bottom, think about the length of that rectangle is variable. It's changing no matter where you put it, right? Here, that height, that R value would be really small, and over here it's really big. So basically, it's whatever the Y coordinate is, you know, at that top location, minus the Y coordinate down here. So sometimes I'll even label these ordered pairs and say like, okay, well, this is some random XY ordered pair. And this ordered pair down here is some random X, but the Y coordinate is always 0. So we're basically just subtracting the Y coordinate. So R, I'm going to say, in this case, is Y minus 0, which I'm going to substitute right now because, you know, y is really x squared. That's my rule. If I have a rectangle drawn in a vertical presentation, my integral should be all in terms of the x variable. So that's a way of describing what that r is. Now, in this particular case, you know, this is a dx integral, and I'm going to go ahead and just set up my disk method here and say, okay, I'm going to find the volume. I'm going to take the pi and move it outside. I've already got r. I've got the dx in there, and then I'm going to find my limits of integration. So remember, these limits of integration I'm going to find off the x-axis. So that means I'm going to start at x equals 0, and I'm going to end at x equals 4. Okay. So that is an integral set up to find the volume. Like, this integral represents the volume of this solid that you've just created. Now, to actually crunch the numbers, we can certainly do this. You know, you have x squared. I don't even really need the minus 0 in there, right? So I can get rid of that. And then x squared squared is just, well, x to the 4th. And this is a pretty friendly antiderivative. So again, I'm kind of pulling the pi off to the side here. My antiderivative is 1/5 x to the 5th. I will put a, it should be a 2. Sorry, my limit of integration here should be a 2. I don't know where I got 4 from. Change that. Okay, so let me go back and explain that. Because you're starting at x equals 0, you're probably wondering, what is she doing? You're ending at x equals 2. That's your stopping point for this integral. And so I'm just going to carry on with my definite integral down here. Make sure I don't forget that pi. And then throw the 2 in. Throw the 0 in. And so your volume is actually 32 pi over 5. That's the actual value of the volume of this solid that you created. All right, so we'll go through a couple more examples. And again, you don't have to like prove the formula. I just wanted to show it to you. So when you do an actual problem, you're just going to kind of write down everything I have on the left, right? You're going to do your shaded region. You're going to identify the disk method and then just kind of walk through setting up that integral, and then you evaluate that definite integral. Okay. So let's go to our next example, which again, I already have drawn in and shaded for you. So I've got that. And what I'm going to do is just sort of talk out that shaded region. And I've got the volume of the solid obtained by rotating the region in the first quadrant. That's an important feature. Bounded by, again, y equals x squared. You see that drawn in. The y-axis, right, that vertical line, and the line y equals 4. So again, y equals is a horizontal line. And so I shaded it. They were the ones that said, oh, it's only in the first quadrant. That's why I'm not shading the section over here. Okay, so that's your first step, is saying, okay, I now know what that region R is. That's really important. It's almost like you want to stop at that moment that you see the word about, right? Like, just stop right there. Find your region, shade it out, and then you're going to decide, well, hey, where am I spinning? Well, in this case, we're spinning on the y-axis, which again is one of your boundary lines. I like to bold it out so I know exactly where I'm spinning. I even put my little spinner in there. And I'm going to follow the rules of the disk method, which, again, I'm going to draw this rectangle in the shaded region that is perpendicular to your axis of rotation and also touching the axis of rotation the whole way through. So perpendicular to the axis of rotation looks like this. There is nothing special about where I am putting it. You could put it higher, you could put it lower. Maybe I'll outline it a little bit so we can really see that rectangle. There it is. There's my perpendicular rectangle drawn in here. And I always imagine these like endpoints, right? You got an endpoint there, an endpoint there. And let's think about it. This is any xy ordered pair that lies on the parabola. This one over here, the x coordinate is always 0, but the y coordinate varies, right? Depending on where you draw it. So I have it drawn in. I'm ready for the disk method. Again, when you take this horizontal rectangle and spin it around the y-axis, you actually create this disk down here. Okay, so what I'm going to do is set this up and say, all right, what do I need to know? I'm going to be using the disk method for sure. And so that means my volume is going to have a pi on the outside. I'm going to have r squared. And this is a dy integral because it was a horizontal presentation. What that means is right now I can fill in my limits of integration. I'm going to start building, you know, if I had that horizontal rectangle, it would start down here at y equals 0, and it would go all the way up until y equals 4. So all I have to do is figure out what R is. So if I kind of go into my picture here and try to identify what R is the length of that rectangle. That's R. So R here is going to be, think about it as right minus left. A lot of what we did with area just transcends right in here. It's really a difference of x coordinates, right? This looks like an x coordinate of like 1.5, x coordinate of 0. Just subtract those, right minus left. So really your R value here is x minus 0. Now, let's think about this. You can't really leave it like this. Remember, that's a dy integral. This should be all in terms of the y variable. Now, I know that this is off of the parabola y equals x squared, so what I have to do is I have to dig in here, and I have to say, okay, that's my equation. I need to rewrite this to say x equals. So I'm just going to use some algebra, and when you take the square root of x squared, you get x. You do have a plus or minus over here on the right. Now, I'm going to choose the y to be positive root y, because all of my y values are positive here in quadrant 1. So that allows me to come back here and say, okay, I know that the radius length was right minus left. I translated that to the x coordinate minus 0, but now I'm going to actually say, hey, it's supposed to be in terms of y. There it is. Let me set up my integral, and let me go for it. So my volume is going to have the pi on the outside. I'm squaring r, which is really just the square root of y, right? I don't really have to write the minus 0, although you can. It's a dy, my limits of integration we already discussed. So this is great. If I said, hey, set up an integral that represents the volume of the solid, you've got it. This is great. All the nuts and bolts are here. Now, if I said find the volume, which is what this question says, now we have to actually just evaluate this integral. So methods of integration are really, really clutch. So the square root of y squared is just y. This is a pretty nice process here for our volume. I'm just going to come up with my antiderivative, 1/2 y squared, 0 to 4. Now again, I don't want to leave the pi out, so I'm going to throw that in. And then I'm going to evaluate that definite integral. 1/2, let's see, 4 squared, that would be 16, minus 1/2 0 squared, which is 0. And so that leaves me with a final answer here of 8 pi. Here is the volume of this solid. All right, so the first two examples should be regions that you can, sketch on your own without too much trouble. They're basic parabolas and lines. This one's a little much. I'd probably give you the picture. You definitely know what the sine wave looks like, but the square root of sine, it's a little much. That's not something that you studied in advanced algebra or pre-calculus. So here is the image. Like here's me giving you, hey, here's what the square root of sine x looks like. And we're talking about the interval here from 0 to pi. So I'm just going to label the graph. Obviously, here's x equals 0. You can kind of reasonably figure out that's pi because it's a little bit more than 3, right? Because pi is 3.14 in value. So again, I'm gonna take the volume of the solid by rotating the region. I'm gonna discuss that region again, bounded by y equals the square root of sine x and the x-axis, just from 0 to pi. So there it is. You've got two equations. You get the square root of sine x, you've got the x-axis, and specifically stated from just 0 to pi. Let's find the volume of that when I rotate that. Again, you're kind of putting a break in your brain here. I already have my region described. Now I'm going to spin it about the x-axis. Okay. So what I'm going to do is come back once again, coming back to what the disk method is. Remember, I'm going to draw a rectangle in the shaded region perpendicular to the axis of rotation. That is also touching the axis of rotation. So I'm just going to get in here and do that. And let's go ahead and highlight it. Maybe I should use a different color. But there's my rectangle. It is perpendicular to the axis of rotation. It is touching the axis of rotation. It is consistent, meaning the top endpoint of that rectangle is always on the square root of sine x, that function, and the bottom of that rectangle is always anchored on the x-axis, which happens to be your axis of rotation. So this is great for the disk method. So what I'm going to do is mark up my picture a little bit and say, okay, well, what I need to know. I need to know what R is. How do I describe R? And so really this is a vertical presentation, which tells me a whole lot about my volume. I know that it's going to be pi r squared dx. That decision has already been made because if it's a vertical presentation, it's a dx integral. Now that means I know my limits of integration are starting at x equals 0 and building out all these rectangles until you end at pi. And so I'm going to fill in the pieces here for that r. Let's think. This ordered pair at the top is any random ordered pair, x comma y. But this ordered pair at the bottom, well, x could be anything, but your y coordinate is 0. You're on the x-axis here. So if I want to describe, like, what's the value of r? What's the length of that rectangle? It's really just basically top minus bottom, which I'm going to write as y minus 0, which I know this integral is supposed to all be in terms of the x variable, so that's great. Let me switch it over. What does that mean? That means r is really the square root of sine x minus 0. Let's go ahead and fully set up my integral to represent this volume and sort of walk it out. So if I asked for an integral that represented the volume of this region of the solid, you have just done so. Here it is. This represents the volume. If I actually said, hey, find the volume, well, now you have to evaluate this. So I will do that. The square root of sine squared is just sine. So again, basic integration techniques are certainly helpful here. And so the integral of sine is negative cosine. I'm going to evaluate that first at pi and then at 0. So that would be negative cosine pi and then minus negative, I'm going to change that to a plus, cosine of 0. And that gives me, let's see, cosine of pi is negative 1. So negative 1 is 1. Cosine of 0 is also 1. So that means your volume is 2 pi. That's the volume of the solid numerically. Okay, so again, what's the shape? Well, it kind of looks like a football maybe, but you knocked this out of the park with disk method. So again, disk method is the method where you draw a rectangle in the shaded region perpendicular to the axis of rotation and happens to be touching the axis of rotation the entire time.